Okay, hello everybody and welcome back to the stream. So previously we've worked on conversions and adding more types and so on, and I want to continue that and start preparing support for pointers. I believe this can be really interesting to add to the interpreter because the Lvalue interpreter is entirely memory safe. It can check whether an address is valid and panic if it isn't, so it's possible to write C programs that use pointers, run them in interpreter, and have them execute without any segfaults. Instead, everything is memory safe, it panics, and so on. So I believe this can be really cool. But before we can start working on that, there are some edge cases we need to tackle regarding Lvalues in general. For example, an assignment like the following, 42 equals 11, obviously is not allowed because 42 is not an Lvalue. You cannot assign the number 42, it's not a variable. But we are compiling it just fine, and then code generation crashes. So we need to catch that appropriately. The standard says that an assignment operator shall have a modifiable Lvalue as its left operand. So this is where the name Lvalue comes from. It's something that can be on the left of an assignment. And we need to check that. So what is a modifiable Lvalue? It's defined here. An Lvalue is an expression that potentially designates an object. So something like an identifier is an Lvalue, or a dereference pointer. And a modifiable Lvalue is an Lvalue that does not have array type, and does not have an incomplete type, does not have a const qualified type, and if it's a structure, it cannot have const qualified members. So let's write a check for that. If we go to the AST, so Lvalues is a property of expressions. So we're writing a function that for an expression, bool is Lvalue that takes a pointer to an expression, and bool is modifiable. Modifier, is that how you spell modifiable? Modi without E. Modifiable Lvalue. And then we implement them like right here. So, and we can like check one by one whether or not the standard says that something is an Lvalue, but I think I can implement it without looking at it. So currently the only thing that is an Lvalue, a function call expression, would be an Lvalue in C++ if it returns a reference. Since C doesn't have references, it can't be. So the only thing is an identifier expression because that resolves to a variable. And then later when we add the dereference operator, that will also be an Lvalue. And like similar like member access and so on. But for now, the only thing is an identifier expression. So return dryad now it has kind identifier expression. Okay, so identifier expressions are Lvalues. Even things like, for example, the assignment operator in C++ is also an Lvalue because it returns a reference. This is explicitly not the case in C. So, but it is not an Lvalue. So an assignment operator is not an Lvalue. And I don't think anything else is an Lvalue either, like the comma operator. Footnote, the comma operator does not yield an Lvalue. So only identifiers are Lvalues. And then we want modifiable Lvalue. What was that? Modifiable Lvalue does not have array type, does not have incomplete type, does not have a const qualified. We don't have any of those, so just check that it is complete, so not void. But I'm guessing, right, you can't have an anyways. So it is an Lvalue and is complete object type. The type of the expression must be complete. Okay. And now in the compiler, when we create an assignment operator, we do a conversion, and there's a to-do. We need to check that we're having an Lvalue. If not, is modifiable Lvalue, the left-hand side. Then we create a warning, rather than error. Log CMOP diagnostic kind error. LRS of assignment is not modifiable. Lvalue. So annotation, kind primary. I just use the location of the assignment here. Finish. Now we're getting the correct error message. Okay, great. Let's commit that. Check for Lvalues in assignment. Let me see. Is no. Oh, we can actually do that. Oh, and we actually. Okay, so we can actually do a couple of to-dos that we missed last time while we added. So we need to promote the type for unary expression. What does the standard say for unary expression? Sorry that I'm getting sidetracked, but this is something that we forgot last week. So let's just clean it up. Unary expression. What is it? Plus value of its promoted operand. Promoted operand, promoted operand, and then this one does not do promotion. Okay. So I believe I have a function integer do integer promotion, right? So child do integer promotion state location child. So we do integer promotion and then we use it. So if we have something like test.c in char I equals 42 plus I, and then we are doing a promotion here. So we're converting the I to signed in 64, which is the integer promotion, and then we're using it. So that works. Do integer promotion for unary operators. And then there was another to-do that we can handle easily, implicit conversion and return type. So expression do assignment conversion. So like this is actually what does the standard say? I'm assuming it's like that. So statements like here. Is it a jump statement? Yes. Return statement. The value of the equation, different type, as if by assignment. So expression, we are doing an assignment conversion. The location is the, do we say that the location for the error message is the location of the, let's just use the location of the return type. So the position that we're having like here, the target type is the current function type return type, and the value is our expression. And this takes care of the error message as well. So now if we do something like return I, then we would do an correct conversion here. Previously, this would generate an error, but now we're doing a conversion. If we do something that isn't compatible, like return void I, cannot do implicit conversion in assignment. This, as I mentioned repeatedly, is a Unicode error in the nworms terminal emulator. That's not our fault. This could be nicer. The error is misaligned because of this garbage here. Like, we could underline more of it, but yeah, I'm not too worried about it at this point. Maybe at the end, if we're really motivated, we can improve all those error messages. Okay, handle implicit conversions in return statement. But now let's actually add what I wanted to do, increment, decrement operators. So we're having 4 kinds of those. We're doing this with prefix increment right here. All right, so we're having then like 2 precedence levels, the postfix one, and then here the prefix ones. And the postfix ones, I believe they are actually Lvalues. Right here. So we want real or pointer type. Interesting, you cannot increment complex numbers. Modifiable Lvalues, right? And then the value of the operand, we increment it as a side effect. We have some sequence operations. I believe if we implement it naively, this will just work out, so I don't want to parse all that. Blah, blah, blah. And then it says somewhere, is this an Lvalue? No, it's the value of the, interesting. So they're not actually Lvalues in C. They're Lvalues in C++. So that's interesting. Okay, so they're not Lvalues. Don't need to worry about those. And then the prefix one, oh, right, those are the ones that are potentially, right. Prefix one, yeah, those are the ones that are actually Lvalues, right, because they return the new value. And they return the old value, right? Decremented also doesn't say that it is an Lvalue. So apparently they are not Lvalues in C. Okay, so let's implement them. I believe since they're essentially all doing the same thing, even though like one does the increment first and the other one after, it makes sense to add them like as its own thing. To just group them in with all the other unary. So we've got a unary expression right here. I believe it just makes sense to add them right here since they don't really have any special semantic, right? They have a side effect, which the other one don't, but I believe, yeah, it's still fine to add them here. So we have pre-inc, which is this one, pre-dec, which is this one, and then post-inc, post-dec. Okay, let's follow the compiler errors. We need to print them. Pre-inc. Decrement. Decrement. We need to generate code for them. So pre-increment. This does the increment and then it returns the new value. So that one's actually, let's put a pin in that, get there later, do the easy one here. So unary up pre-inc, post-inc, dec. So what's the type they should be? They should be like real arithmetic types, but I don't think I will ever plan on adding complex numbers. So it's just arithmetic. And then when we add pointers later, we need to adjust this. So we want arithmetic types. Right, so, okay, so this does the type checking. I'm assuming they also do integer promotion. See the, yeah, probably like, see the discussion of additive operators right here in compound assignment. So this one, single evaluation, like I'm assuming we're doing pointer. All right, equivalent to the assignment, to the addition. Addition does like the usual integer promotion stuff. Actually, so we're currently doing integer promotion, but I believe we need to do like the usual arithmetic conversions. Oh, no, we don't. So what this is saying that plus inc is specified, so plus temp. Standard says this is the same as that, and the standard says that is the same as that. Right. And for a regular addition, we need to do the usual arithmetic conversions to make temp and one this a common type. Right, so this works out. Like if temp would be like a char, then one, both of those are converted to signed int. But since we are not doing the one, like we're not explicitly creating a literal one here, we don't need to do any conversion on there. And the effect is that if we assume that the one, the right hand side, automatically has the right type, then all this function does that we're supposed to be calling at this point. Like if we assume right hand side has the correct type already, then all it does an integer promotion on the left hand side, and then we're assuming that we're having the same type. So this is equivalent to doing the integer promotion. So let's write that down in a comment. For increment, decrement, we need to do the usual arithmetic conversions between child and the number 1. However, if we assume that 1 already has the correct type, this just does integer promotion on child. So we can just call that instead. For the other unary operators, integer promotion is what we need to do anyway. Okay. So now we're correctly type checking these. Of course, so we need to handle codegen and we need to parse them. Let's parse them first, since this is right here in the same file. So we've got unary operators right here, and the unary operators, they include the prefix version. So we can add a new operator, clove unary op pre-inc, lexilit, and unary op decrement, like so. And then we're having a new postfix op. This still creates a unary op, and this is the post version. Unary op post decrement. Okay. There might be some parsing ambiguities. Let's see. So I did some modification right here. So let's just make the compiler happy. Post inc pdec post dec clove to do implement. Okay. And let's test out that we are parsing things correctly. So we want a variable. Let's set it to 10. Then we want to assert that if we do that, we enter with 11, and afterwards I is 11. If we're doing that, then we want 11, but afterwards I is 12. If we do that, we want 11, and afterwards I is 11. And if we do that, we want 11, but afterwards I is back to 10. And right, the clang format doesn't know what's going on here. Now matching function to call object of type CLove expression. What? This is not a nice error message. Oh, right. I know what's going on here. So we're adding postfix unary operators. And we are having here a callback that takes, which one is it? This one that takes an operator and then a child, like a unary operator and then a child. But for a postfix version, this is actually swapped. At first passes the child and then the operator. So this is annoying. Like we need to write a version that takes a child and then a unary operator, but I don't just want to delegate to this lambda. But I can't do that. So I need to extract that into a function, which is annoying. Oh. Why is it? No. So let's copy you. Paste you in here. CLove expression. Create unary, like so. Remove this comma. And then here return create unary state of child. I can do that. Like so. Okay. Okay, so we're parsing a bunch of things. We've got a pre-increment. Let's open the file first. So we've got a pre-increment from I and 11, right? And then we've got assignment, we've got a post-increment. So that seems to work fine. We're triggering a bunch of to-dos. And then we got a certain failure since we're not doing anything. And the tests still pass. Okay, great. So let's try and handle culture. So the issue is that those modify the operator. So at this point, the value of the of its child, so the current value of the expression has been pushed onto the stack. However, we don't want to be we need the address of the child variable in order to modify it. So this is similar to what we're doing with assignment. Where do we do assignment? Right. So for assignment, normally when we evaluate an expression, we're getting its value. Right. So when we evaluate an identifier expression, what we're getting is we're loading its value onto the stack. But for assignment and also for increment, we don't want its value, we want its address. So we have got this function right here, which evaluates the left-hand side of an assignment operator and gets its address. So we need the same function to handle the unary operator. So let's extract it. The thing is, we don't only want its address, we also need its type. So let's say it's let's create a struct Lvalue. So on Lvalue, never mind. So we want a function that returns the type, codegen Lvalue, const CLove expression. Okay. Right here. Okay. And then we're returning that. So what this function does, it evaluates the expression as an Lvalue and returns its type. Okay. This is probably I've apparently killed my language server again because this doesn't apply. So let me get the error messages. Cogen Lvalue. Right. So we don't have the left-hand side, it's just called expression. We don't have the local variables, we don't have b. Yeah, so we need the local variable. So b, first of all, is just context builder. That's easy. And then we need the local vars. They're right here. So let's pass them in as parameter. Let's just, yeah, let's stuff them into the context. So variable decl local vars part of the context. So then we can conveniently access them whenever we need them. Context local vars. We clear them. Is lookup not? Oh, right. So this can't be a variable decl because they can also be a parameter. So it was correct that this is just a decl. Context. Right here, we're calling a new function. Cogen Lvalue context left-hand side. Okay, so that still works. So now we can use this function right here. So for a pre-increment, we don't care about the existing value. Since we need to return the old value, the new value anyway, so we just pop it from the stack. So pop the top value of the stack. This isn't any performance, right? It will just remove the instruction that created it, so that's fine. Then we load, get the address of the variable of the Lvalue, cogen Lvalue context. Then what we want to do is we want to push. So now we got the address. We need to load its value. So we load it. Then we load it. Then we push the number 1. uint 1. It doesn't matter whether it's unsigned or signed, it's the same one anyway. And then we are calling like the arithmetic op. We have a function to get the appropriate somewhere. Call arithmetic built-in. The built-in that we want to call is clof binary arithmetic op add, and we've got the type. Yeah, so the type is the same. So that type, so we're calling add. And then we want to store its result. So we need to duplicate it. What's the instruction called? Pick. So we duplicate the top value, and then we are storing it again into the field. But for that, we also need the address again. So we need the address twice. So we duplicate it here. And then I need to duplicate this one, and then I need to modify the stack. Okay. Let's just see if that works, and then I'll comment that. So what does pre-inc do? Which line number is this? Line 5. So line 5. We are getting the address. We're loading its value. We're pushing 1. We're calling add. We are duplicating this value. We are getting roll 1, which is like this local address. We're dereferencing it, and then we're storing it. That is correct. However, it doesn't do like normally when we generate the code, it does, so to store something, we're calling local address. Then we're calling deref, which checks that the address is valid and gets a pointer to it. This is the index of the field, and then we can call store. But for storing a value, we instead have this optimization, which indexes it directly based on the offset, which is a lot faster since the offset is given as the argument. So statically, we don't need to do any verification that the address is correct at runtime. And the optimization doesn't trigger if the address comes from a role instruction as opposed to a literal local address. So it's actually faster if we are not duplicating it, but instead loading it twice. So actually, we don't need to load it since we already have it. Okay, so that's a lot simpler. So we already have the current value. We're just adding 1 to it, duplicating that value and storing 1 copy into the Lvalue, and then this is the one that we're evaluating. Okay. So that is simpler. So we're loading the value, we're pushing 1, we're calling add, and we are duplicating it, and then we're storing 1 copy into the value back. Okay, so add 1 to the current value, save a copy into the Lvalue. The result, we leave the new value onto the stack. And for decrement, this is exactly the same. We're just doing a different operation. So pre-dec. So if you're having pre-increment, then we're adding. Otherwise, we're decrementing. Like so. Okay, so now we're handling both pre-versions. The post versions are the same, but we are storing a different. The only difference is the thing that we're evaluating is different. So we duplicate the old value as we want to evaluate that. So we duplicate it. Then store the new value in the Lvalue. This removes it from the stack. At this point, the old value is on the stack. Let's unify the comments. Okay. So the only difference is the value that we're evaluating, but otherwise we're doing the same thing. So the assertion fails. Let's selectively comment things out to see which assertion. Oh, right. The assertion fails because here we're having posting. Test passes. So let's walk through the code so we understand what's going on. So this line 5 is ++i. We're loading variable I. We're pushing 1. We're calling add. We're duplicating the new value and storing a copy. And then we are comparing it. Okay. For post increment, the only difference is that we're loading the value, which is line 8. Line 8. So we're loading the value, then we're duplicating it, doing addition and storing the result of the addition back in the value. But we still have a copy of the old value on the stack, which is what we are evaluating and comparing it. And then for the decrement, we're just calling subtraction instead of the other one. So that's good. The only thing left to do is, I believe we need to catch this case, right? This one triggers an assertion failure. So we need to check it, create unary right here. This one has to be arithmetic and modifiable Lvalue. Great. Add increment. Do I use add all the time? Yeah. We add increment decrement operators. Okay. Let's tackle pointers. Let's start adding pointers, see how far we get. So pointers. This requires adding a new type, a pointer type. So we are adding a new kind of type, which is a pointer type. A pointer type is like a function type in that sense. So pointer type. So it has a pointee type, which is the type the pointer points to, and this is our child. And then we get a getter for the pointee type. Oh, interesting. Apparently, so we are printing. Unfortunately, we don't get any errors, so we need to add a bunch of types here. So when we clone it, pointer type. What we want to do, create a pointer type by cloning recursively the pointee type, like so. Pointers don't participate here. Pointers we handle the same. We handle is void, is signed int, is unsigned int, is integer, is arithmetic, is scalar. So pointers, I believe, are scalar types. Where does it say that? Types. Signed integer type, extended integer type, decimal floating point complex, char, a number of derived types. Arithmetic type pointer types are called scalar types. Or diet node has kind. Pointer type. Pointers are scalar, pointers are complete, pointers don't have an integer rank. That is fine here. Then I need to write a hasher for them. So we only need to hash the data that isn't stored in the tree, which is nothing for both pointers and functions, because the only data is the tree relationship, which is fine. And then likewise for equal, they don't have any data beside the tree data. So that is that. Okay. Then we want to format pointer types. So right here, when we dump a type, manually want to build up its child. Type node kind visitor const of pointer type type. Let's just print a star and then visit its pointy type, which means that I can just do that. So we want to dryad container visit event traverse event enter. So we want to visit it first and then we visit its child. Okay, so this will print a star and then whatever is the type of the child. If it's a function type, it's a bit annoying, so let's put a space in there. Right, this is not the correct C++ syntax anyway, so we just, whatever, doesn't matter. That. And then we also need to handle types right here. So when we code gen a type, so we need to return a love type for a pointer type. And this is pretty easy because this is just the love type value. So the pointers fit in the default type that we also put on the stack. So that is very straightforward. And that is all the infrastructure needed to handle type. We just need some way to create this type now, and this should be good to go. So pointers, to create a pointer, we need a declarator. For a pointer right here, declarator. So we've got a declarator is an optional pointer. This part we now need to pass. We don't have any type qualifiers like constant volatile. So this is just before a direct declarator, we can have an optional list of stars essentially, and each star creates a new pointer. So when we pass a declarator like here, so we're currently supporting function declarators. Let's also support pointer declarators. So pointers, this is a prefix operation, right? You have a star and then we're having something. Okay. So the operator, we're getting using that tag type, and this is just a star. And the operand is a direct declarator, which can include, so actually this is something like so. So the operand is a function declarator and pointer declarator. I'm not sure whether that works, but let's try it out. So state clove. We're getting the op tag first, which is pointer declarator, and then we're having a child. And then we need to create a pointer declarator right here. So this represents a name with a star. And then of course we need to add that. So we need to add that to our tree. So we've got name declarators and function declarators. We're now also having pointer declarators, declarator kind of pointer. We're having a single child, which we're inserting. Right, so. And need to update the enum value right here. Need to update this one. Need to update those functions. So for pointer declarator, we're also forwarding to the child. They don't have an init, but here when we have a type, do we actually do something? Namely, we get the type of the child, get type types decor child. Wait, what? Where do we get the decl? Oh, right. So we're getting right. So this is the base type, right. So the child type. Recursively getting the child of the type. Child decl type. So this gets the child of the type, and then we add a pointer to it. So dot create clove pointer type. We need to clone the child type. Like so. Okay, I'm a bit confused what the language server is complaining about it. That should creator. Where do I? Oh, right. Return types. So we need to build the type. Type build. It's a bit confusing because of the internally we can't just create type nodes because we don't want duplicates. So we need to create a lambda here that is called with something that can create a type and that knows how to destroy it if it's a duplicate of an existing type. It's not the best API. I'm missing some right here. Okay. Right. So it compiles. Let's actually see what happens. So int star I. So the way a declaration is composed is we've got this part here. This is a type. And this part is a declarator, and it consists of a pointer declarator followed by a name declarator. And if we just have a name declarator, the type is just the type. But when we have a pointer declarator, it will add a pointer type to it. And we are missing some type somewhere. Right here. So this creates a non-init declaration. So when we have a pointer declarator, we are still creating a variable. So when we pass a declaration, and as long as we don't have a function declarator, we're creating variables. However, when we're creating a variable of a non-pointer, we're checking that we have a complete type. And when we have a pointer, we don't check that because we can have pointers to incomplete types. So that's actually nice that it just falls out. And it appears to work. So we've got a variable I, which has type pointer to signed in 64. And we're creating storage for it, which is 8 byte in size, because that's the size of our pointer. So that's cool. We can also do like a void pointer because we're not checking for complete types, right? So now we're creating two variables. What happens when we assign them? We're not handling it. So let's handle it. Wait. Oh, now it's going on here. I need to add you here. Actually, surprised that it worked before. Cannot do implicit conversion in assignment. Nice. Because an int pointer and a void pointer are not assignable. This one should work. However, since actually both directions work in C, since you can implicitly convert between a void pointer and everything. Okay, so let's handle assignment properly. Let's restart so get the language server again. I don't know what's going on there. If I write to like weird code, the language server crashes and then I have to restart them. Okay. So I actually now found the place where this is specified. So assignment has a bunch of constraints about what the types, what type combinations are allowed. And then it just says it does a conversion. So those are the constraints that we need to check. And what we're currently doing is implementing this one. We are having arithmetic type and arithmetic type, which is this one. We need to add a new case when we are having this pointer type are pointers of compatible types. Let's skip this one, implement this one first. So left operand is some sort of pointer type, and the other is void. And we're having all the same qualifiers. So this refers to like constness and so on. Left operand has qualified or unqualified null pointer. Right, we don't have null pointers at the moment. So left operand has atomic qualified or unqualified pointer type. And one operand is pointed to an object type, and the other one. So if the left hand side is a pointer, let's start there. Else if let's actually add a pointer version just for consistency. So Cloud is pointer. Pointer type. Like so. There was I right here. Else Cloud is pointer. So the target type is the left hand side. And then we're having either compatible types or one is void. So if Cloud is void, so I need the dereferenced type. So if the left one is a pointer, can the right side be something that isn't a pointer? It can be a null pointer constant or null pointer. Right. So let's say if both are pointers. Value type. Okay. Auto target pointee type. Triad node cast Cloud pointer type, target type, pointee type, auto value pointee type. Pointer type, value type, pointee type. So if one of those is void, we're good. Void target pointee type, value pointee type. So then we can cast between them. Target type, value. Okay. So that's the sort of conversion that is allowed here. Right? But the code gen doesn't know about it. So where do we do conversions? Not here. Not here. 498. here. Okay, so if the type is a pointer type, Lv is pointer, and the other side is also a pointer, we don't need to do anything. Pointers in Lv aren't typed. So that's a very easy conversion. This is like a reinterpret cast that you would do in C++ to convert between pointers. Doesn't generate any assembly instructions because on assembly pointers aren't typed. And this is the same here, right? We're just loading the value, right, this one pointer, and storing it in the other without any need for conversion. Right, and the other direction also works because this is C. You can convert a void to any pointer implicitly, so that works. Great. So we've got pointers, and we can do assignment between pointers, and this also handles stuff like returning. Let's commit that. Add pointer type. Okay. Pointers aren't really useful at the moment, so we want to actually create variables the other way around, so pointer and I. And the first type should pass, so this part should pass correctly because this is like a pointer declarator and then an I. Right? It's not nice style, but it just works out. So let's add address of operator. So the address of operator, what does it do? It's a unary operator. Here. So that much I know. Unary operators, address and indirection. The operator shall either be a function designator. Okay, let's not worry about function pointers at the moment. We don't have those, or an Lvalue. That is not a bit field. We don't have bit field. We don't have register. Okay, and then it yields the address of the operand, has type pointer to type. Alright, so this just says that if we take the address of a dereference operation, that's actually a no-op. Interesting. So you can actually like, interesting. That is not what we were about. Okay. So, and I believe the parsing one is just, yeah, it's one of the unary operators. So parsing is straightforward. Compiler. Unary expression. Unary right here. So we've got a new kind of operator. Unary of address. Lexi lit address. And then when we create it right here, address. So do we have any constraints on the type? But the operand, right, it must be an Lvalue. So return Lv is Lvalue. But the type can be anything. We are not actually doing integer promotion here. So let's start introducing special cases. If opt is Clv unary op address, we're doing something. Else if opt Clv unary op L0, we're doing something different. Else we're doing this. So now I can simplify this code. For an L0, the type is always int. Unary expression log state as create built-in type. So int of child. Do we do integer promotion in that case actually? I don't think it matters, but let's just do integer promotion. So CodeGen has less cases. We're doing integer promotion here. So CodeGen, actually we need to do it. We need to do integer promotion as it's defined in terms of which does integer promotion. Okay, but for the address, we're doing something different. So for the address, we don't need any conversions on the thing we're taking the address of, and the type is a pointer type. So state as types build. So we're getting what's it called? C-node type forest node creator, and we're returning pointer type cloning the type of the child. So we need to clone the type because the tree is intrinsically linked, as we can't have the same node both as a child and outside the child. And then we are just creating the new node. Unary expression location type of child. Okay. So this is the address of operator, at least the part that doesn't have CodeGen. Address, like so. And this is the part that does CodeGen. And the all we need to do is we need to get the address of an Lvalue. And this is pretty easy because we've written a function for that. CodeGen Lvalue context expression child. And we want to, by this point, we've already evaluated the expression, which means we've gotten its value. So we're just popping it from the stack. So remove the value of the child expression and push its address instead. This isn't like it. This wastes a bit of like we're going through all this trouble of generating code that evaluates the expression, and then we're just discarding it. But that should be optimized away by Loaf, and this might have consequences with like stuff where we do, as the standard says, unstar pointer. This is a no-op. But by this point, we've already created a panic if the pointer is invalid. So this might be something that we need to fix. But I'm not worried about that right now. And hey, that seems correct. So the else is correct. We have an assignment expression where the right-hand side, we are taking the address of I. And here in the code, we are getting the local address of our variable 1, which is the one where I is stored. And we're storing it at offset 0, which is the one where pointer is stored. So that is correct. We've implemented address of. At address of operator. Of course, the other puzzle is Dereference. So this is also a unary operator. Must have a pointer type, and we just dereference and get an Lvalue. Okay, so let's add it. Unary expression deref, like so. This is an Lvalue, so we need to update its Lvalue. So if we are having an identifier expression, return true. Else if auto unary, try add node, try cast seal of unary expression, e return op unary op dereference, else return false. Okay, so this is an Lvalue. That takes care of that. Then we need to update the print code right here. So we want to print it. Unary expression. Added a bunch of those already, so just star deref operand of a deref right here. Deref, we must have a pointer type. Is pointer. And then we need to special case it. Because the type is, we actually want to remove the pointer type. So the type, again, we need to handle interning. We need to, actually we don't. So the type is just the child has a type, which we know that it is a pointer type. Node cast seal pointer type. So we can get its pointee type, which is the type of our expression. Unary expression, location, type of child. Let's complete the example. Pointer 42, seal of assert I equals 42. Right, need to handle it in CodeGen. And this should be pretty easy. So to dereference it, the address is on top of the stack. Load its value. So load field B, we get its type, which is the type of the expression, and currently everything has just a single field, so we hardcode index 0, and we forgot one case somewhere. Ah yeah, right. Interesting. Oh, because we are using it as an assignment, which is, let's test the simpler thing first. So I equals 40. So we're not supporting it at an Lvalue at the moment. We've just implemented code for that. So we dereference it, and we're getting an invalid address. That is interesting. There shouldn't be an invalid address. So let's see what's going on. Line 7. Line 7. We are loading the value stored in the local variable 0. We are dereferencing it, and then we're loading the value from there. So we are storing, interesting, we're loading it. So this loads the local variable at index 0, which is correct. This is our pointer. And here we're storing the address into our local value at 0, which is our pointer. Interesting. So this should work, right? Since we are storing the address of the variable 1 into the pointer. So let's debug what's going on here. I'm assuming it's a bug in low. We are printing pointer. Because when we print it, right, so it has the value 2. And it is not considered to be an address. Is it supposed to have the value 2? I don't think it is supposed to have the value 2. The address would be a different value. Let's simplify the example. And let's actually debug this. Code gen. So somewhere assignment expression. Right. So what I want to do, I want to set the breakpoint in this function. So this is the function that's executed to store the value, I'm assuming. Apparently it isn't. Oh, it isn't because it's optimized away. Okay. No, SSC. So store local value right here. This one's called. Okay, so this is the function that's supposed to store our pointer into memory. So we're getting the what is on top of our stack. So we are currently executing this instruction right here. And on the top of our stack is the value 2, which as address is allocation 2, generation 0, offset 0. So why is this allocation 2? It's not supposed to be allocation 2. It's supposed to be, let's set an earlier breakpoint. Okay. So we are currently attempting to execute the local addressing function. Right, I see where the bug is. So the way this works, every allocation has an index, and the index of a local variable allocation is given by an offset based on the first local alloc of the stack frame. So the first local alloc of the stack frame is 1, and then we're adding the offset 1, which is specified in the instruction. So right, this is the offset 1 because we want to store the local variable at offset 1. However, I've implemented an optimization where variables whose address is never taken are never added into this list of allocations. So the pointer variable, we don't take the address of the pointer itself. So this isn't added into the table of allocations, which means that this doesn't participate here. So the offset here, the index, should be 0 as opposed to 1, because this isn't added into the table. So the offset here is wrong, which is why we're creating an invalid address, so it isn't recognized. So I need to fix that. And I believe the easiest way to fix it is to go into the builder code as a builder. So somewhere in here, we're adding local storage right here. So here we're generating instructions that create the variables. But I need to update the right. So the issue here is that this needs to increment the index still. Actually, maybe the better way is to do So when we execute the local storage instruction, right. So here is the, when we create a local allocation, we add that to the list of local allocations. We're not doing that when we do the local storage, which is an optimization. This saves we don't need to go into this array and so on. But we still need to reserve space for it. Right, so this pushes it to a table and so on. So I believe, so the correct fix is probably to then, when we detect that something is a storage and not an address, is we need to go ahead and update all the indices to be correct, which is annoying because then we need to loop over all the local address instruction and update the index manually. So let's not do that. Alternatively, we could just reserve space for the allocations and fill them. But I don't think I can implement that very easily into the stream right now. So instead, let's just disable this optimization. So if we disable this optimization, instead of local storage, we're creating a local alloc, which means that we're now having a correct address. Okay. Maybe if I have time, we can fix that properly later. But for now, this works. And this means that now the pointer is set to a correct address, which means this one should work. Great. So this works. The second part is using it as an Lvalue. So for that, we need to implement this function codegen Lvalue, because we have a second type of Lvalue, which is a unary operator. Unary expression. And this is a const pointer. And since so if it's an Lvalue, essentially, this is interesting. So normally when we evaluate something like this, what we get is the value what pointer points to. But when we want to evaluate it as an Lvalue, essentially we want the address of the instead. So to evaluate a pointer as an Lvalue, we don't actually want to dereference it. We want to push the address onto the stack, which is just the value of the pointer. So what we're doing is we need to recursively evaluate the value of the expression. Right, which isn't something that we can do right now. Okay, so what we actually need to do is we need to call a function like codegen expression context. So we need to evaluate the child expression, which is which pushes some address onto the stack, which is the Lvalue representation of a pointer. So I need to write a function that evaluates an expression. So void codegen expression context expression, which essentially is the same as this one, but instead of valuing the body and taking care of all these statements, we just need to take care of the expression. We don't need to create identity declarations, just expressions. Right, so. And then right here. So all the code that handles of expressions just calls this function. There are many expressions. Okay. So via traverse event, we just want to handle them once. Expression, expression, and then we're just calling codegen expression context expression. Let's see whether we broke something. Apparently we broke something. Why did we break something? We shouldn't trigger this code. Right, we don't trigger this code. So all I did is just push that into the expression. Maybe visit tree doesn't handle the top level expression. It should do that. So visit tree, yeah, it calls begin, and when I traverse something, okay, apparently this should handle the correct one. Interesting. Huh. Oh, because this recursively. So I believe I need a node child visitor here. So we don't want to visit the children manually. I believe that was part of the issue. Seal of node kind is the type. Right. So what's going on is we visited the first expression, and then we manually visited the children, which I guess triggered like some sort of variable decrement. Something goes. Okay, but we haven't broke something. We haven't broken anything, so now we can test the use as Lvalues again. Right, all tests pass. So we can now take the address of variables, dereference them both in an R-value context where we're just reading it and in an L-value context. And this is what I meant line 9.5. So to like the assignment, what we're essentially doing is we're taking the address and then we're just immediately storing something in there. Whereas if we use it as an R-value, we dereference the pointer by loading the value stored on the pointer. So which is a bit weird because like if we actually use a pointer, we want to dereference it, but for assignment, the star does nothing, which is okay, but that works. And so this is now entirely type safe. So I can do this, return the address of a local variable, memory safe, I mean. Initialize pointer by that. And oops. Be not parsing this correctly. Okay, we are completely handling this one. So let's do it like so, just to demonstrate. Okay. So this, I need to call cool. So this is like the dereference operation here isn't allowed because pointer stores a local variable that has since been deployed. and this is what the VM detects. So because all allocations are stored in a table, and when we remove from a function, they're marked as freed in the table. Before we dereference it, we can check, we can ask the table, hey, is this still a valid pointer? And if not, we panic. So it's impossible to get like a segmentation fault using loaf, even though we are executing C code, because it's completely memory safe, because yeah, it just falls out. Great. So let's commit that. At deref. Did I already commit the other one? All right. So add deref operator. Let's really quickly see what's going on in the parsing. So it doesn't like it when we have a function that returns a pointer type. Right. Probably because the declarator parsing code doesn't work correctly. Right. So to actually see what's going on here, we can do the following. So this is a parsing bug, and Lexi provides a way to debug parsing bugs. Lexi trace. I don't know the argument, so let me get the language server back. Oh, it's not Love, it's Lexi. So Lexi trace. We want to trace the production translation unit. I'm getting. So what are the arguments? File is to standard out. Input.buffer state. Okay. Then we've got an error because that we need to add, this is not a great error, but I know what's going on. So function declarator. So we need to give those, need to specify a correct name here as well. Function declarator. Pointer declarator. So now we're tracing the parsing code, which means that Lexi tells us exactly what it is doing at every point in the parse step. So, and actually let's Lexi visualization flags, make it fancy. Make it fancy, please. Okay. Much better. Okay. So we are parsing a translation unit. We are having a global declaration, type specifier list void. That part is correct. And then we're parsing an init declarator list, which consists of an init declarator, which consists of a declarator, which consists of a bunch of operation chains. So we've got the literal star, and then the right-hand side is foo, followed by, right, so at this point it detects, finishes the operation chain function declarator, whose left-hand side, right. So there's a function declarator consisting of foo and parents. That is correct. And then here it has the operation pointer declarator, whose operand is a function declarator and two stars. So that, I believe, is actually correct. So the actual error, only functions can have a declaration. Right, so this is, so what we're having is a pointer declarator, but whose child is a function declarator, right? So what we actually need to do to fix it is, right, so we've got to get name here. const function declarator get function. Similar to get name. Because when we're having a name declarator, that is a plain variable and not a function. So here we're returning null pointer. When we have a function decl, we're returning itself. And when we're having a pointer declarator, we're returning the function of its child. In a declarator can't be a function as well. I actually just might be due to an error, so let's just be close here anyway. So get function decl child. And then here, const function declarator. Like so. I don't know what you're complaining about. So here we're calling it function decl list value font. Okay, did that help? Okay, parsing continues a lot further, right? So this trace mode is really cool because we can see everything, like when it backtraced and so on. And this now works fine, which means I can write the example a bit nicer. Int I return its address, int pointer who, pointer 11. Okay, we also need to handle the implicit conversion here. Currently we're not doing that, but we don't need the trace mode anymore. Do assignment conversion. Interesting. Why? Oh, right. If they're the same, then we're also good. Right, but this should be handled by this case. Why aren't you handled by this case? Of is pointer target type. So the target type isn't a pointer. What? Oh, I think I know what's going on here. So when we are getting where we're getting this function code, right? So we're getting we are ignoring that we're having a pointer declarator initially. So this strips away the pointer declarator, so we are no longer having a function that returns a pointer. So we need to keep that information around. So the declarator is the decl list value.font, and then this is the function declarator. So the function declarator is null, then we're getting the name from the full declarator, and we're getting the type from the full declarator. But we're getting the parameters from the function declarator. Like so. Okay. So the type is not a function type, really? Why is the type not a function type? Oh, right. Because the type is a pointer to a function. Okay, there is something, something isn't right the way this is passed. Because now the type is a pointer to a function. I don't think we're parsing it correctly. but I'm out of time. So I have to leave it right here. We'll pick that up. I don't think I'll be streaming on Thursday. There are planned internet outages. So we pick it up next week. Made a lot of progress. Thanks for everybody who stopped by, and until then.